We're going to begin the illustration with an example of a culvert. And so what we see here on screen right now is the top view. And this is the best depiction I could put together in a few minutes that's showing there's a roadway going over a stream. And this stream is rectangular. The channel is a rectangular channel that has a width of 5 meters. And so if we were looking at the cross-section of it, that means it's 5 meters in width, the stream. The way the HY8 keeps track of distances, both lengths of culvert and lengths of roadway, is with stations. And this is actually common in transportation engineering where roadway lengths are being specified, that they'd say something like 5 plus 0, 0. That just means that it's sort of like a location datum. And so what this is showing is, you know, here the roadway, maybe this was a certain part that was put in by a contractor. They had to begin paving at 5 plus 0, 0. And here at 5:35 is where we actually begin the crossing. And so that means that the roadway station at the end of where the stream and the road are on top of each other is 5 plus 40. This slope that's listed here, that's the channel slope. And so that's 0.25% channel slope. And we're going to have to put that into HY8. In addition to calculating the hydraulics of culverts, it also does a really nice job calculating the stream hydraulics downstream of the culvert. They call it the tailwater. The headwater is the flow upstream of the culvert. Tailwater is the flow downstream of the culvert. And you can see from the red arrow here, that's indicating the direction of the flow. Here's a cross-sectional view. This view that we're seeing right here is if we were to cut the culvert in this direction. So if we had a line right here and then we're looking sideways, you can see that the culvert is 20 meters long. You can tell that from the inlet station and the outlet station. We know the invert elevation, so that means the bottom of the culvert opening is 300. And then to specify the slope of the culvert, we have to identify an elevation of the outlet. And so although we do tell the program the slope of the channel, you can see that the slope of the channel is 0.25% from this. We don't tell the program directly the slope of the culvert. Instead, we tell it the elevation of the culvert's opening and exit, and then we also tell it how long the culvert is. And so from that, it's going to itself calculate the slope of the culvert. One of the really important things is to know how high off of the channel bottom the roadway is. And why do you suppose it's important for us to tell the program the elevation of the roadway height? Well, actually, yeah, I mean, you'd prefer that the water not get this high and start going over the road, but sometimes it's okay. They call it overtopping when the flow goes over the top. And sometimes the specifications for a Department of Transportation or a municipality would say that the water should go through the culvert in like a 10-year storm, but a 25-year storm can go overtopping. And so it maybe will be okay, maybe it's not okay, but in order for the program to be able to identify how much of the water goes over the road, it has to know the elevation of the road. So we're going to also enter that information in. And in addition to just knowing the elevation, it's going to want to know a lot of information about how wide is the road. It's going to want to know the length of the crest, because when overtopping is occurring, it sort of looks like a weir, flow going over the edge of that roadway. And so now here we've got our channel. Think about the water level. Here's a culvert, a circular culvert, and then here's the road. Okay, so think about the water level is this high. The water's only going through the pipe. If the water level goes up to here, then the water is flowing over the top of the culvert, and simultaneously it's also going through the pipe. And so there will be some flow through the culvert barrel and some flow over the top of the road. So we have to specify the length of the crest, as it's called, the channel width, and the elevation.
Does the slope, like even if there's a straight slope of
the road.
Would there be two different slopes before the culvert and after the culvert?
You mean of the channel?
Yeah.
Well, it doesn't matter the upstream as much. There could be a different channel slope upstream of it, but it just basically looks at the water right at the front face of the culvert, and it doesn't do a lot of calculations upstream of the culvert. And so if the water level is getting deeper and deeper and deeper, you can assume that it's definitely choking the flow in the upstream direction, but it's only doing tailwater calculations, not headwater calculations. So it doesn't need the upstream slope. Maybe it'll be the same, maybe it won't. It doesn't have to be different. All right? So I'm going to do this first one as an illustration. We've got several examples today where I'll ask you to follow along, but this first one, what I suggest is just watch what I do. Don't try and follow along on this one, just so you can see where the buttons are and how I enter all the information that's needed. So I'm going to create a new project and add a culvert crossing. That's the default option. The minimum flow, I want it to do its analysis all the way from 0 to, in this example, I expect my design flow will be 25 cubic meters per second, but I want to take a look at what's happening all the way up to 30. And so it'll perform the analysis from 0, oh, and here's a problem, CFS, and the units here are cubic meters per second. So I need to change the units. Let's change from US customary to metric. And then I want to, again, add a new culvert crossing. All right, so now everything's in CMS, which is cubic meters per second. So 0, 25 is my design flow. 30 cubic meters per second is the maximum flow. Now, tailwater data. This is really nice. If I had showed you this tailwater calculator during hydraulics, you would have really liked it because it can calculate like the depth of flow in a trapezoidal channel super fast, and it doesn't have any trouble at all. It gives you a really nice curve of the depth, the flow rate, and so on. This is a rectangular channel, though, 5 meters wide. So let's say it's a rectangular channel. The bottom width is 5 meters. The slope is 0.0025. And then the roughness of the channel, the N value for the downstream, let's see, no N value is specified here, it looks like. Let me change that so that in future semesters I've got an N value. Let's have this be N is 0.05. So that's a relatively rough N value that would be typical for, you know, cobbled rock, and 0.05. The channel invert elevation that it's asking for here is actually, it's asking what is the elevation of the downstream channel where it matches the outlet of the culvert. Now this is an important point. They don't have to necessarily be the same elevation. In this drawing they are. The channel and the outlet culvert is the same elevation, but it could have been that they don't match up. Maybe I have, here's the channel, and here's my culvert, and the water's coming out of the culvert, but then there's a drop. And so sometimes I could have the channel invert be different from the culvert outlet invert. So be aware that you can identify an offset for those two. In this case, they're the same. Okay, so I'll go into here, and it's asking for the channel invert, and that is 299.95. $299.95. Now if I click view the rating curve, the calculations it does is for a certain flow rate, how deep is the water in that channel. So it finds this by Manning's equation. It's just simply solving Manning's equation for depth at a variety of different Q's. And if I wanted to, I could copy this, Control C, and then paste it into Excel and put together a really nice curve that shows the tailwater, a tailwater rating curve as it's called. So just to show you that this data pastes really easily, I probably could have highlighted the column titles as well. Let's see if that'll copy the titles now. Maybe I'll have to type them. No, I'd have to type them. But this is the flow rate, this is elevation, and this is the depth. It also calculates the velocity and the shear stress. So the shear stress analysis might be useful if we know the strength of the soil downstream. It could tell us we're running into a situation where the movement of the water is scouring the soil. But the main thing as a hydraulic engineer that I'd be interested in is flow rate versus depth. So that's the tailwater. So, I mean, what does it mean? It means that when we get up to 25 cubic meters per second, which is my design flow rate, the depth of the water in the channel is going to be 3.8 meters. It's 5 meters wide, and downstream of the culvert, under normal conditions, steady flow, the depth Y is going to be 3.8 meters. So hopefully the channel itself is at least that deep, 3.8 meters. And let's go back to the drawing here. It looks like it probably is because the roadway is up at 307, and usually the roadway is at the same elevation as the surrounding channel. You don't usually go up as you're going on a culvert sometimes, but it's usually made to be the same elevation as the surrounding ground. So I think that the channel is going to be able to accommodate that flow is the good news. All right, so now we have to start putting in the information about the roadway. There's two options to begin with, constant roadway elevation or irregular. And what that's asking for constant roadway elevation is that we're assuming that the road, well, if we look at it in this view, the front view, constant roadway elevation means that the elevation is, I haven't drawn it very level, but the roadway is just a flat surface like this. Sometimes culverts will be in a sag, though. Sometimes maybe a culvert, here's a, you're going down on the road, and then the road starts going up, and there's a channel at the bottom, and here's the culvert. And so maybe what we'd want to do is specify what the roadway looks like in that kind of a way, where we'd identify X and Y data, and we could have an irregularly shaped roadway elevation. The simplest option is the default one that it gives you is just a constant roadway elevation. Now, first roadway station, if we go back to the drawing here, this roadway station thing isn't really important. Let me think. If we're using it just to identify, yeah, the roadway station, actually, this first one here doesn't matter really. So we'll just say the first roadway station is the 500. Now, crest length does matter. That is asking how long is the crest length when there's overtopping. And here it's 5 meters. Since it's a rectangular channel, the crest length will be the same as the channel width. If it was trapezoidal, they'd be different. Think about if we had a trapezoidal channel like this, and here's the culvert. So maybe if it was 5 meters wide at the bottom, and the water rises all the way to the top of the road, then we'd have to know what are the side slopes in order to find crest length. So crest length is when the water's at all the way to the top, what is the crest length? And so if it was like 1 to 1, then we'd want to know how high does the water go when it starts to overtop, and then find out each of these side lengths on the edge. So that's the difference between a trapezoidal and a rectangular channel for crest length. This is just going to be 5 meters since it's rectangular channel. Crest elevation is asking what is the roadway elevation. So that's 307. Paved, or you can have it be gravel, or you can pick a discharge coefficient to correspond to the roughness. And then top width is asking how wide, maybe like how many lanes are there. And so what would you estimate is the width of a 2-lane road? 24 feet. So if we say that's maybe 4 meters, it would be a good estimate of how wide it is. All right, so we'll put in 4 meters is the top width of the crest. Now finally, the culvert data. The example is asking the question, would a 24-inch diameter culvert be okay? Now all the rest of this problem is in SI units, and so let's convert that 25-inch over to millimeters. 25 inches is approximately 625 millimeters. That would be the equivalent. So let's say we're going to input a circular concrete culvert that has a diameter of 625 millimeters. Embedment depth is something that we won't generally have to mess around with, but it has to do with, in the cross-sectional view, if the culvert is into the fill or if it's projecting outward. We'll just leave that blank. The Manning's N, it picks based on what the culvert's made out of. If I said corrugated steel, then it picks a different Manning's N. And you can override the default value that it chooses. 625 was my diameter. It's a straight culvert. Inlet configuration gives you some options having to do with whether there is a pipe barrel sticking out, if there is a mitered edge, if it has wing walls. These are all different inlet configurations that correspond to a different amount of energy loss at the inlet. So I'm going to just leave it at the default square edge with head wall. That means that there is a concrete face. Actually, in this drawing, it looks like these little triangles here indicate that there are wing walls. So I'm going to have it say, I don't see the wing wall option. Maybe. All right, well, we'll just leave it at square edge with head wall. Inlet depression is something that can be used to reduce the accumulation of trash through the culvert. If there was a small little, they excavated and took out some material right before the water goes into the culvert, like you put in just a little pan here, then trash and sediment can accumulate in that pan instead of in the culvert. They call that an inlet depression. And we're going to say that this doesn't have that inlet depression. It's not shown on the drawing, so we'll leave it at no. And finally, the inlet station, inlet elevation, outlet station, that is telling the computer the slope of the culvert and how long it is. And so the inlet station is 1 plus 0, 0. The outlet station 1 plus 2, 0. That tells us that it's 20 meters long. So I'll say 100 and 120. So now it knows it's a culvert length of 20 meters. And then the elevation here, 300 and 299.95. Okay, so 300 and 299.95. That's all the information it needs. We can have it now analyze the crossing or just click OK. Here it's showing where the water elevation will be when it begins to overtop. Analyze crossing gives you a report that says what the headwater elevation is doing as the flow rate increases. And it tells you that when overtopping begins, like the water level gets all the way to that top of the road rate, it gets to the top of the road when only 2 cubic meters per second are getting through. So that culvert obviously is nowhere near big enough. We have this 24-inch or 625 millimeter culvert. And if we want to be able to get 25 cubic meters per second through there without any overtopping, we need to make it much bigger. So it takes a little while to get used to looking at this. One of the good reports, let's see, is it the culvert summary table? One of them, okay, here's the depth. So this is telling you the depth of the water on the front face for a certain discharge. So you can either look at it in terms of elevation or depth. You know, if we know the elevation of the inlet is 300, then we can just say that this is 7.2 meters of depth. But sometimes it won't be some even number, so it's nice to look at the inlet depth. So the conclusion here is the culvert's too small to convey 25 cubic meters per second. And so the nice thing that this allows us to do is just iterate, because we can change it from 625, let's say that it's 1,500 millimeters, and analyze it again. Now we can get up to 11.8 cubic meters per second before overtopping begins.
Take all that information and throw it in Excel.
Yeah, what do you mean? Well, you can, yeah, you can copy and paste. Like if you wanted to keep a record of, you know, I used 625 and it gave me this, I used 1,500 and it gave me that. You can copy and paste, yeah. It also has a number of different reports. It'll create a report, but I think those are overused. HY8 report. You know, sometimes in the homework I'll have a student that will just give me the report, and it doesn't really have the answers, you know. Let's see, is it still building the report? All right. I make a special note in the homework assignment that if I ask you a question, don't just give me a printout like this, but you have to actually answer the question and identify where is the answer on the page here. So if the question was, what's the flow rate when overtopping begins? Well, you can find that out from the table. The flow rate when overtopping begins is 11.8 cubic meters per second. But if you're turning this in for assignment, circle this on the table and then write in your handwriting below, overtopping begins at a flow rate of 11.8 cubic meters per second. Don't make the grader search for the answer on the report that you provide. So it still needs to be bigger though. If we want to get 25 cubic meters per second without overtopping, we have to make the culvert larger. And so maybe 2,000 and analyze the crossing. Now we're getting pretty close. Overtopping doesn't occur until 20.6 cubic meters per second. And I can change it again. Well, we're getting to the point where this is a very, very large culvert. Maybe we can't have one that big. Maybe only we have available 1,500. So we can have in 2 barrels. So 1,500, and then number of barrels means, do you want to have 1 pipe, or we can change this to say 2 pipes. And so now there are going to be 2 pipes. Each of them are 1,500. And we can analyze the crossing with that. It carries 22.6 before there's overtopping. If we put in 3 barrels, that ought to do it. In fact, that'll be plenty of capacity. The question is, would we actually have space for 3 barrels? Analyze crossing. Now we're fine, because we want to get 25 without overtopping. And what this shows is that when you go all the way up to 30 cubic meters per second, you have 29 cubic meters going over through the culvert, and then 0.2 is flowing over the top, over the roadway. And so very little overtopping will occur even at the 30 cubic meters per second. Okay, so that's the demonstration I wanted to show you before turning you loose on the first example that you're going to do yourself. In this example, we have a culvert that is a 1.5 meter by 1.5 meter box culvert. It's made out of concrete, so here's the end value. Now the data that you've gathered from the client or in the field, you know the slope of the channel is equal to the slope of the culvert. And you know the length of the culvert, but you haven't been given any station information. And so actually what you're going to have to do is synthesize that. You know, the program asks you to define the culvert length by telling it stations, and so you're going to have to make up station information. This is the same channel as before. It is a channel width is 5 meters, and it's rectangular channel. And it's also a 2-lane road going over the top, the same as in the previous example. But what we're going to do is we want to find out what flow rate causes the headwater to equal to be 2. So if I was asking that question on the previous example, then I would have to find out when is the headwater equal to 2. And so here you can see the inlet depth is 2 when the discharge is 15. And one way that I can actually get even closer to the more resolution is if I can say, I'll do the analysis from, what was the flow rate, by the way, when I just looked at it again? 15? Okay, so if I do the analysis, instead of 0 to 30, if I do it from 10 to 20 and analyze it, then it will do this in 1 cubic meter per second increments. And so I can find out more easily what headwater depth gives me a certain discharge. 2.05 gives me 15 cubic meters per second. So in this example, number 2, it's asking you to find out what flow rate gives you a headwater depth of 2 meters. Okay, so I'm going to stop talking and let you start inputting this information into HY8. I'll be circulating around in case you've got questions about the geometry or how to use the program. What? Boy, I'd have to take a look. I've never heard of that not being there. Have you got version 7.2 or 7.3? Probably 7.2. It's all right. You don't need it. Invert, what did I write? 99.7. Remember, all this roadway data is irrelevant because in our analysis we don't care what happens during overtopping. We want to find out what happens before overtopping when the headwater depth is 2 meters. And it's going to be concrete box, what did I say, 1.5 by 1.5, so 1,500 by 1,500. Outlet 140. This is culvert 40 meters long. So it's asking the flow rate will cause the headwater depth of 2. Inlet 2. 6. So 5 to 7. So the question asks, what flow rate causes the headwater to get up to a depth of 2? And it looks like it's about 5.7 cubic meters per second. Because when I'm at 5.6, I'm a little bit below. When I'm at 5.7, or 5.8, it's a little bit above. So maybe a little bit less than 5.7 is the flow rate that causes the headwater depth to be equal to 2. Flow that will cause the headwater depth equal to be 2. Channel width equals 5. Was everybody able to get that first part there? To do an analysis and get the report from that analysis? The analyzed crossing table? The entry table? Yeah, let's talk about the data that I put in. Some of it is, I just picked it. Some of it is important that has to be the same. For example, in the problem, in the given information, it doesn't tell you these elevations. And so I just said, by definition, I'm going to have this be 100, and then everything else, like the roadway elevation and the outlet elevation, comes from this decision to say, you know, let this be. So you could do the same problem and say 200, and this would be 109.72, and this elevation would be 203. You'd get the same results. Or you could say, let this be 0 elevation, and then this one would be 0.28, and this would be 3.28. But what is important, the things in here that have to be this way is I have to have the bottom width equal to 5. I have to have the channel slope of 0.07. That was given. The Manning's N, we said it's the same channel, so 0.05 would correspond to like a rough, rocky channel. And it's rectangular and channel invert. I picked that because I say that the channel, the two things that come together here, the culvert and the channel, have the same elevation. By the way, it's a little bit confusing to have it say outlet invert because it says out and in at the same time. So invert means at the bottom, and outlet means the water coming out of the culvert. So it's saying the bottom of the culvert at the outlet. So here's the inlet, here's the outlet, and instead of saying top and bottom, for culverts, they say crown for the top and invert for the bottom. And I don't know why they don't say top and bottom, but they say invert and crown instead.
Where it says culvert type, it's straight.
Yeah.
It says inlet type, it says conventional, side taper, slope taper.
Just use the default value unless you know some specific information about like that it's mitered or that there are wing walls. In the homework problem, I ask you to play around with these culvert type options and inlet configuration because you'll get a little bit different results if you change these around. Like, let's look at the analysis. Right now it's the default straight and square edge, analyze crossing, and it takes about 5.7 to get up to the headwater the depth of 2. So about 5.7 gives me the depth of 2. But what if I change the what if I change it to side tapered and beveled with a wing wall? The wing wall is supposed to reduce energy loss, so hopefully I should be able to get more flow rate, and the depth won't increase as much for the same flow rate. So analyze crossing. Face width must be greater than span. Side taper must be before 4 and 6. So side taper. Let's see if straight will get it to work. I still want to have the wing wall though. All right. So if we look at the results, analyze crossing. So now I have more flow rate going through for the same depth. Remember, before I put in the wing wall, I was only getting about 5.7 when the depth was 2 meters. Now for a depth of 2 meters, I'm getting about 6.3 cubic meters per second. So playing around with these options here gives you some ability to increase the flow rate. All of this discharge data is only telling the problem when to begin the analysis, what flow rate to begin the analysis, and what flow rate to end the analysis. Basically, the range of flow rates that you're interested in taking a look at. It doesn't actually change the hydraulics of the situation. It only changes what Q value it plugs into the discharge equations. Are there other questions about this example? All right. Let's change this back to square edge. The Manning's end of the concrete channel, 1500 by 1500, will go from 5, 6, and 7. From 5 to 7. The roughness of the channel, let me analyze that. Okay, I'm back to where it'll be about 5.7.
Mine says it's only 100.6.
All right. Okay. Let's take a look at the geometry of your culvert. Oh, well, you've got trapezoidal channel. It looks like. What was that we were just looking at here? Weird. Yeah. It's a strange shape. Let's see. Yeah, the difference isn't jumping out at me.
And the only thing, you had a 4 here, I have a 5.
Like a top width?
Yeah, but I didn't think the roadway stuff mattered.
Yeah, since we're, let's see, analyze possible. I'd have to look at it more closely. I don't know. When in doubt, just start from scratch. Okay. So, yeah, delete the culvert and put in the crossing again. Let's move on to the second example that you're going to work. Let's take a look at the conditions it's asked. Oh wait, no, we had another part of this question. So part B, what is the rectangular channel width that causes the tailwater depth to be 2 for the flow rate found in part A? So the flow rate for part A, the Q that we found was 5.7 cubic meters per second. That is what causes headwater to be equal to 2.0 meters. Okay. Now, the question it's asking is, well, what about the tailwater? How wide should we make how wide can the channel be to cause that depth to be equal to 2? Right now, if we take a look at the tailwater, the depth isn't getting anywhere near to 2, up around the 5.7 flow rate. So we can make the channel much narrower than the 5 it is currently. If we just want to play around with things, so we can make the channel width, let's see, 3, and have it calculate that. And now the depth at 5.7 is 1.4. So we could make it 2 meters wide and take a look at the tailwater. So we're actually getting really close now. It says that for 5.7, it's about 2.2 meters is the depth. So that's too much, and we need to make the channel a little bit more wide again. So if we say 2.5 and look at the tailwater, this is the downstream data. The depth is less than 2, and so we can iterate just back and forth, 2.25, finding what width would ultimately give us a depth of 2 meters that corresponds to the flow rate of 5.7. So between 5.6 and 5.8, we're trying to get the depth up to 2. And so it tells us that if all we ever expected is 5.7 cubic meters per second, then the channel doesn't necessarily have to be so wide as 5 meters. We could afford to make it more narrow. That's the point of part B. Repeated iteration of the tailwater rating curve, trying to find out what flow rate causes the depth of flow to be equal to 2. All right, let's look at this last example for the day. We have a culvert length of 40 meters. And if the culvert length is 40 meters and it's straight up like that, that probably means that the roadway width is also going to be 40 meters. So now we have trapezoidal instead of a rectangular channel. One-to-one side slopes, it's carrying 10 cubic meters per second. And so design a culvert so the maximum headwater is 7 meters. Now you're going to have to iterate the size of the culvert to try and find out if it starts to overtop at 8, but we only want there to be 7 meters of headwater depth in order to carry 10 cubic meters per second. So how big should the culvert be to carry all of that flow? And then the second part of it is, or design a culvert where you're allowed to have 1 cubic meter per second of overtopping. Here's the crossing data that I've put in for the second example, where now we have a trapezoidal channel with one-to-one side slopes, and we are going to have to design the culvert, and we're trying to limit the headwater to 7 meters in the first part of this problem. Now I'm just going to take a first look to see if a single 1,500 millimeter diameter circular corrugated steel pipe will work. It probably won't, but you have to start somewhere. If you want to choose a different type of culvert, that's fine. You know, you can pick any sort of design that will convey the flow, limiting the headwater to 7 meters. In fact, that's too boring. I don't want to start with the circular one. I'm going to go with a pipe arch, and they have all these standard sizes of pipe arches. I want to have a number 4 pipe arch. Okay, so it tells the span and the rise of that arch. It's made out of steel, so it picks the end value of it. Now the inlet station and outlet station, that's how you define the culvert length. It's 40 meters long, and the elevation of the inlet and the outlet tells it the slope of the culvert. And the slope of the culvert here, again, is the same as the channel slope. So I calculated 99.72 by multiplying 40 times the channel slope, and then I subtract that amount from 100. That's where I got 99.72. Okay, so I'll just do the analysis, and it looks like the question is, how big should it be so that the maximum headwater is 7 meters, carrying 10 cubic meters per second? So when I get up to 10 cubic meters per second, actually, there's a lot of overtopping. So this size that I chose is too small. It's not big enough at all. So let me try and pick a bigger one. What if I chose a number 7? And we'll analyze what happens with a number 7. Okay, so I've got the, let me just choose number 7, analyze. Now it's overtopping when it's carrying 4, so we're getting closer, but it's still not large enough. So I'll choose number 10 and analyze it. Getting pretty close at this point. It's, oh, hold on a second. No, yeah, it's carrying all of the flow. So what this is saying is it's at 107.33, so that's just a little bit too deep, because what I want to have is I want the headwater depth to be 7 when it's carrying 10 cubic meters per second. So just a tiny bit bigger will be able to mean that I don't go over 7. So if I choose the next larger culvert size. So if I go back into these options and I choose the number 11, that will definitely do it. Okay, so analyze. Now it shows me that actually I only have a headwater depth of 5.15 when I'm carrying the 10 cubic meters per second. So this would do the job. This culvert that we chose, the number 11 pipe arch. Or if you wanted to go with a concrete box and say, what were the dimensions of that number 11? Just to go back to here. So the number 11 was 1955 by 1320. So if I do like 1800 by 1200 on a concrete box, that should also work. So what if I do 1800 by 1200 and analyze the crossing? So yeah, it's plenty big, because now instead of, before it was an arch, what I put in originally was something like this, and it was 1800 by 1200, but now I've made it rectangular, so I've got all this extra flow area. That's why the headwater is only going up to 3. So I can make it quite a bit smaller. All right, I'll give you a couple of minutes to play around with different pipe sizes and try and optimize something. What we're trying to do, the goal in this iteration, is make the discharge equal to 10 and the headwater elevation to 107. Keep playing around with the size of the pipe that will cause the headwater elevation to be equal to 107, or whatever elevation corresponds to a headwater depth of 7 meters when the discharge is 10 cubic meters per second. Okay, so what I did was, when I had this open, I pressed print screen, and now in Word I can just say right click and then paste, and here's the picture. And then, just to make it a little bit more nice, in format I will crop the picture to only include this part. And so now the grader can see this is the data that went into the culvert, and then here is the analysis. If I click OK. All right, so here's the results. I maybe could do print screen again and paste, Control V, and then there is the results, format, crop. So in your assignment, it's asking you to provide screenshots. That's a nice way to do that. All right, so that's all we have for today. Remember that the assignment is due in class at the beginning of class on Tuesday. Let me know if you've got questions, and I'll do my best to help you out. Have a good day.